Hello and Assalamualaikum everyone. My name is Nur Mirza Imanina binti Muhammad Shukri from RAS 2034B. And the article that I choose for this assignment is Stability of Small Vacancy Clusters in Tungsten by Molecular Dynamics. For the introduction, Frankel pairs, a type of lattice point defects, are introduced by high energy radiation in the process of cool down phase. The majority of these flaws mutually eliminate one another. It is typically believed that surviving vacancies group together and create 3D voids to minimize their energy, but surviving interstitially typically group into planar objects which collapse into energy efficient prismatic dislocation loops. The next section focuses on tungsten, which was selected for IPER's diverter because of its high melting point, good heat conductivity and good sputtering resistance. In reality, the remaining vacancies are more likely to form dislocation loop and planar clusters platelet in addition to void, giving them greater potential than interstitial. As compared to dislocation loops, it has been demonstrated that the voids in tungsten are energetically more favorable than half 0.11 and 100 loops up to critically size of 6 multiply 10 vacancies and 6 multiply 105 vacancies respectively. The visible limit for voids in transmission electron microscopy (TEM) is approximately 1 nanometer. Detected small gaps in tungsten at the limit of TEM visibility that were created during irradiation at room temperature. Additionally, 1.5 nanometer voids in tungsten that were exposed to radiation at 500 Celsius and subsequently annealed at 800 Celsius for a whole hour. The starting point of the abnormal precipitation of rhenium in neutron irradiated tungsten at high temperature, 900 Celsius, can be understood in part of studying the first principle inquiry in combination with Monte Carlo simulations. After an hour of annealing of temperatures between 400 to 1300, tungsten was exposed to radiation at low temperature and low dose utilizing positron annihilation spectroscopy (PAS). They noticed that the density of vacancy clusters significantly decreased at temperature of 800 Celsius and above. A similar decrease of void size and concentration was observed at 1122 23 Kelvin by PAS. For the first problem statement is, what are the structural properties and arrangement of small vacancy clusters in tungsten? Second is, how does the cluster size composition influence the stability and dynamic of vacancy clusters? And the third is, what is the effect of temperature on the thermodynamic stability and migration behavior of vacancy clusters? The objective of this study is to investigate the stability of small vacancy clusters in tungsten using molecular dynamic simulations. For the methodology, the study employs molecular dynamic simulations to model the behavior of tungsten vacancy clusters. Interatomic potential accurately describing the tungsten system are utilized to simulate the atomic interactions. The simulation consider varying cluster size, compositions and temperature to capture the effect of thermodynamics and kinetics on cluster stability. Advanced analysis techniques such as radial distribution functions, coordination numbers, and energy calculations are employed to investigate the structural properties and energetic of the vacancy clusters. Next is result and analysis. This figure showed the formation energy of the vacancy clusters in W divided by the numbers. The dashed line is given by equation 1 using an average surface energy of 0.230 electron volt. It appears that the small vacancy clusters with n less than 9 are not correctly described by free surface energy, probably because they are closer to point defects. The scatter of formation energy is probably mainly caused by the random phasing introduced by intersecting the sphere with the BCC lattice. Indeed, in reality, the void surface will be faceted preferentially by 110 planes, where the surface energy exhibits a minimum. Other factors explaining the scatter include the unconsiderate edge between phases. Typical results of a single molecular dynamics are reported in Figure 2 for 15 vacancy clusters at 1860 Kelvin and Figure 3 for 27 vacancy cluster at 2063 Kelvin. In the case of 27 vacancy clusters, the formation energy cannot be reliably used as the dissociation criterion, as it initially decreases and later oscillates. It is probably due to the simple way the void was created. It should be noted that we rarely observe the motion of the whole vacancy clusters. When it is observed, it seems that it is often related to rejoin events, which are also infrequent. In Figure 5a, the resulting dissociation energy as a function of number of vacancy increases with number of vacancies steeply at the beginning and then tends to saturate. In Figure 5b, the characteristic temperature at which the cluster dissociates in 1s as a function of the number vacancy. It exhibits a similar behavior and is qualitatively comparable. Both the 65 and 89 vacancy clusters dissociate somehow more easily than expected. Lower stability of these clusters is probably due to our simple spherical constructions of the voids, which are not necessarily the most stable voids. For the next table is all the fitted parameters are summarized in Table 1. A dissociation barrier of 1.0 electron volt, while our value is lower at 1.19 electron volt. They observe qualitatively the same behavior of the characteristic temperature as with an increase with the number of vacancy and at higher number of vacancy tendency to saturate. They report a characteristic temperature for 1300 Kelvin for 9 vacancies and 1600 Kelvin for 15 vacancies, while we have obtained 790 plus minus 250 Kelvin and 1050 plus minus 19 Kelvin respectively. Kinetic Monte Carlo (KMC) used with simple Kang-Weinberg model and vacancy migration barrier of 1.75 electron volt obtained by DFT. On the other hand, the MNB potential used here gives a lower vacancy migration barrier of 1.52 electron volt. Consequently, they observe lower stability of vacancy clusters. Moreover, molecular dynamics and KMC use completely different timescales and also different criterion to distinguish dissociation and rejoin events. A dissociation criterion of 100 steps used, but these KMC steps are variable and temperature dependent. For our simulated large voids, we found that the dissociation energy saturates at 3.5 electron volt and the 1 second characteristic temperature saturates at 1200 Kelvin. Size of this void corresponds to nanovoids at the limit of transmission electron microscopy (TEM) resolution. From the calculations, these nanovoids are stable at room temperature. If extrapolates the obtained values to a time interval of using annealing of 1 hour, then these nanovoids will lose a vacancy in 1 hour at 700 plus minus 200 degrees Celsius. This corresponds well to a decrease in density of vacancy clusters. After 1 hour annealing at 800 degrees Celsius observed by position annihilation spectroscopy (PAS), the created voids are not thermally most stable voids and the start of a void dissociation, not the complete void. For the conclusion, vacancy clusters are dissociated by molecular dynamics and have developed a solid dissociation criterion. It has been discovered that thermal activation causes the void dissociation at high temperature. For larger vacancy clusters, the dissociation energy and characteristic temperatures tend to saturate at 3.5 electron volt and 1200 Kelvin respectively. These values rise with the number of vacancies. Other who used KMC discovered the same qualitative behavior. As a result of the single vacancy migration barrier between somewhat underestimated by the utilized EAM potential compared to the DFT value used by KMC, our estimates for dissociation energies and characteristic temperature are a bit lower. Therefore, in practice, we would anticipate a marginally higher stability for the voids. That's all from me. Thank you.